But I argue that one of the big reasons is that so far over the last sort of several decades, we've sort of set the world of users of this technology into we've sort of split it into two sets of people. One is the programmer who writes the code, and the other is, let's just say, people like me or Professor Bansal, who are people who think of how to build these program analyses or how to build these verifiers. And one person writes the program, and then you sort of throw it over the wall to this verifier, which is of course could be an analysis that's running up in the cloud or some sophisticated thing in your compiler or whatnot. And because of this kind of separation, it's quite undesirable for two reasons. One is that the programmer can't actually influence how verification happens. The programmer is just writing their code, and they can't change. They can't say, no, I don't care about those things. I care about these things. Don't waste my time telling me about those things. I only care about these things. And similarly, the verifier can't really influence the program. They just get to see the program after the fact, and they can say yes or no, but they can't say, if you only change your program a little bit, like so, then maybe I'd be able to verify it. Okay. And so instead, what I've been working on is a way, what I hope to sort of tell you about over the next hour or so, is a way where instead of having this split, you have the verifier and the programmer as separate, what I would like is these two to be the same person. So you, the programmer, or well, if not you, whoever it is the programmer, um, can sort of build the analysis while they program. So your verification or your error checking happens during development as opposed to checking for bugs after. It's literally, I want it to be a kind of an online thing as you're coding, right? And this way, the two things that I hope will happen is A, the analysis can actually change the program's design. So if the analysis can't influence, can't prove something, if you can catch it as you're coding, you can actually make the programmer edit their code immediately, right? And this is not something that I'm speculating about. There have been several papers that came out, at Google and Uber and Amazon and Facebook over the last 5 or 6 years that make this exact point. Okay, so this is a paper by Manu Sridharan from who was at the time at Uber. He says that if you so they had this whole system where they write a bunch of Java code, and then there would be this analysis that would run sort of overnight and sort of up add to their pull request some feedback that says, oh, these Java pointers might be null, and so you must fix that, right? And so they write that this late feedback could lead to a very frustrating experience. The developers change could pass during code review. So during review, everyone was happy, but then sort of 6 weeks later, the null checker comes back and says, "Oh, by the way, there was this error, and you should fix it." And by then, everyone's forgotten, right? The developer has moved on to another task, and they're very unhappy about the whole thing. The same thing was noted at Google. Google developers, so I'm quoting from their paper, Google developers perceive that issues flagged at compile time, so as they're coding, as opposed to patches for checked in code, catch more important bugs. Survey participants said 74% of the issues flagged at compile time are real problems. So it's the same issue, whether you whether it was reported at compile time or later, but just the fact that it was reported at compile time means it's a real problem, as opposed to something that nobody cares about, right? Same thing at Facebook. They tried this batch deployment where it was run overnight, produced bug lists. So in the morning, right, you would get your errors. And when the developers presented this outside their workflow, they were just like, oh, we don't want to deal with this. But so it was literally 0%, right? But then when they switched their tool on to be in a kind of incremental mode so that they could do it much closer, it was not overnight, the fix rate. So it's the same kinds of errors they were finding shot up to 70%, right? So you really want the analysis to sort of produce its results as you're coding so that you can influence, you could just have the programmer change their code as they're writing it, right? Dually, I want the program or the programmer to influence the analysis itself. So I want the programmer to be able to say what they care about. What do I care about in this program? I don't want to just say, well, the verifiers have decided that these are 7 properties that are of importance. I want the programmer to be able to specify various correctness requirements and further even maybe give the tool some hints on how to do the verification, right? So we might start with just checking that if you have pointers, that those pointers remain in bounds. You might want to then the programmer might jack it up and say, you know what, I have some arrays or vectors. I want to check that the indices are in bounds. Maybe I want to check that integer operations do not overflow or underflow. And then I can slowly kind of turn the volume up and I can say, here are some user defined invariants on some data type that I wrote or some data structure. I might specify some security requirements all the way to quote unquote functional correctness, right? I want all of these things to be a kind of knob that the developer can turn and get the analysis to verify as they go. So great. That's what I want to have happen. And I'm going to call this programmer aided analysis instead of program analysis or kind of language integrated verification, either way, right? And next, what I hope to tell you is one path that I've been sort of exploring towards making this real, okay, towards implementing this programmer aided analysis. And in this talk, I'll sort of split it up roughly into two parts. Okay, so the first part, I'm going to talk about the programmer's view. Okay, so you as a developer, how would you use this system that I've been sort of developing over the past decade or so? And this is, I'm going to introduce the notion of refinements and refinement types for Rust. And then in the second part, I will, we'll see how the time goes. By the way, I should keep an eye on the clock. Oh, grief. I should have brought a phone or something. Anyway, somebody will tell me how much time there's left. In the second part of the talk, I will tell you a little bit about how the analysis actually works. Okay, so I'll split this up into two parts. And the second half is kind of the more technical part. And I'm not sure, I'm not sure how much I'll be able to convey. But the first part hopefully is quite accessible because it's supposed to be a kind of imagine you know how to program. Here's a kind of tool that you could use. Okay. And then I'll summarize with some sort of preliminary comparisons, some preliminary experimental results that we have. Okay, so let's jump right in and let me tell you a bit about this notion of refinement types for Rust. So, by the way, everything I'm saying is it's on public on GitHub. So, for those of you who like, you can go and check it out. You can git clone and start running some of these things. But let me jump in and just explain what refinements are and how you as a programmer might use them. Okay. So it's very hard to do a. Let me just pop out so I can. I'm full screen here, and I'll have to break out of this. Oh, I maybe Saurav, you can help me. I'm curious how many people know a little bit about Rust. If you can do a quick poll with whoever is there. I can't see the screen, so I can't tell.
Oh, okay. Yeah, could you please raise your hands?
If
So
you
we
could
have
just raise.
around, yeah, so there are probably like 8 people out of a group of, let's say, 40.
Okay, okay, fair enough. So
Okay.
this will also be a small little tutorial. I mean, for the most part, you can, Rust and for us Java will be interchangeable. But you can just yell if you get confused. Okay. Okay. So here's what we're going to do. Um, I'm going to show you how you can sort of start with plain Rust with just types. You can imagine Java if you like. We're going to use Rust syntax here because that's what the tool is. And then I'm going to start decorating those types with extra things which are going to express contracts or specifications on the code. Okay. Oh God, why is my screen frozen? This is not good. My apologies. Something horrible has happened. Ah, why is this? Oh no. Oh my God. This slide is not progressing. Saurav, can you hear me?
We can hear you, Ranjit. It may just be that you just want to kind of get out of the full screen mode and then get back in.
Yes, let me try that. My laptop appears to have. Oh no. What the hell? This is a new thing. It just literally crashed. I guess I've lost control. Help. At this
We
point,
can hear
usually
you, so it's at least doing fine on the audio front.
it's doing fine, but it is not progressing, and I appear to have lost complete control of my actual. Oh
Mouse. Okay, I see.
no, something. Wait, what is? I may have to reboot or something.
Oh, okay.
Well, this
No,
is a
that's
bit dire. Let's see. What can I do? I can jack up the brightness, but I cannot. Ah, is there some kind of abort button? Hang on. Let's. Oh no, something happened. I'm trying very hard to get out of. What the hell, man? Hang on. Hang on. Oh no. What the? I
maybe you
can't.
want to try unsharing your screen and sharing it back again because I, I'm
I
just
can't. I simply cannot because I guess my screen is being observed. I can't. I've somehow now logged out of my machine, and okay. I'm just going to leave. Oh, I,
Okay, okay,
I,
okay.
I, I might just. This is so strange. What is going on here? Have I been? Okay, I'm just going to come back.
Sure,
See
sure,
you in a
sure,
sec.
sure, sure.
Oh Lord, this is weird.
Yeah, well, it shouldn't gone then. Yeah, this slide should have gone, right? Maybe you can boot him out. Maybe Okay, Ranjit, if you can hear me, I'm booting you out. So at least that has happened as expected. So nothing wrong on our side. Ah, he's there.
Sorry about that.
Okay, great. Hi, Ranjit.
Oh gosh. Well, hang on. Everything has to be. Ah, Lord. This is so weird. Wait, is this even the right slide? Um, Hang on. Navigator. Let me just go to where I was. Oh gosh.
So you'll have to share your
Okay.
screen again, though.
Oh, right, right. Of course. Let me share my screen. Desktop. Just select the window. Let's just select everything. Entire screen. Allow. I wonder if. Hmm, what did I
We
do?
can see your
Is
screen.
everything seen now? Okay, good.
Yeah.
Oh no, I'm scared to start this now. There's no telling what's going to happen. I wonder if I should not make it full screen. Maybe I'll just go like this so I can see
Okay,
the
okay,
rest of my
sure.
stream. I'm a little concerned. Okay, we'll just do it this way, okay?
Okay, okay.
Let me move this out and not make it full screen. Okay, so here's the plan. So what I'm going to do is I'll sort of slowly walk through. I'll give you a little Rust tutorial, and I'll show you how you can start adding refinements as we kind of go. Okay. Okay. Let's. Oh God. Wait. How do I go to the next slide now? This is getting to be a real disaster. Oh, seriously. Okay. Okay. So here's the. Oh, do I dare? Okay, I'm going to try it. Let's just hope for the best. So what we're going to do is we're going to start with, so in Rust, B stands for a base type. Okay, so think like integer or Boolean or something like that. And this V is going to be a refinement index. Okay, so what I'm going to do is I'm going to take base values like int, bool, string, things like that. And I'm going to index it with an expression. You'll see some examples in a second. Okay, for example, um, in plain Rust, you might write I32 in green, which means a 32-bit integer, right? And if I write I32 of 5, that means I'm refining it, I'm constraining it to say not just any integer, but the integer that is literally equal to the number 5. Okay. Similarly, I might take a boolean. So bool is in green is just a boolean, true or false. But I might refine it to say the singleton boolean that is literally equal to true. Okay. So let me just show you a quick example of how one does this. Okay. So I'm going to pop out and let me just spin up this little demo. Okay. So here we go. And please, I mean, I guess you'll have to speak through Saurav if you have any questions, but stop me at any time. Okay. Before the machine comes and stops me. So here is I'm writing a little function called tt, and in Rust this just says I'm a function. It's called tt, doesn't matter what it's called. It doesn't take any inputs, right? So open curly, open close is just a function that doesn't take any parameters, and it returns a boolean. And here what I'm doing is I'm saying it doesn't return any boolean, it specifically returns the boolean true. And look at the body is true, okay? And so the code type checks. If instead I change this body from true to false, then with any luck, if, oh God, one should never do any demos because they never work when you want them to. Well, now it's not working. Imagine that. Oh God, nothing is going right today. What should have happened, cannot find value 2 in the scope. What is going wrong? Why is this not working? Okay, you know what? Um, this was literally working 1 second ago. Split terminal. All right, give me a second, folks. Create new terminal. There we go. Why is this not working? Why is this not working? Let me try reloading this window, shall I? It usually does something. Oh God. Sorry. Okay, suppose I. Oh, I'm so annoyed. Suppose I change that to false. This is supposed to happen automatically, but for some reason it doesn't. Um, anyway, there's no way you guys can help me figure that out. So here you go. You can sort of see what happened, right? Now when I compiled, I wish I could figure this out. But I can't. Anyway,
We can
so
say that if
yeah,
a force condition cannot be proved, so is that not what is expected?
yes, that's expected, correct? Because here I say if I'm returning the value false, then the type checker is saying, well, obviously false is not the same thing as true. Okay,
Right, right, right.
and so that's why I get an error. And so if I change this back to true, and now I sort of rerun it, then it'll say, of course, that's all fine. Okay, this compiles. This is much nicer when. Hang on, give me 1 second. Let me just find out why this wretched thing is not. Um, sorry, this was. I'm very puzzled by this. It was literally working 1 second ago. Enable false, false. I don't know what's going on here. Oh, dude. Give me, just humor me for 1 more second, my friends. I'm sorry. Let me just try a different one. Um, oh man, this is like, this is so terribly embarrassing. Okay, okay, let's try this. Da, 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 da. Oh, good. Okay, well, I'll just use this window. Somehow this one seems to be working a little better. Here we go. Okay, so now you notice when I make that false, I get a little red squiggly because this was supposed to be true. Okay, so let me just fix that back to true. Similarly, here's a function ff which returns bool, and here I'm refining it to say bool false. It sort of type checks. Okay, let's look at this one. Here's a function called bob, takes no inputs, and it returns an I32, 32-bit integer. And here I'm saying it's an I32 that's exactly equal to 45. And in this case, the type checker is clever enough to work out that 2 plus 43 is 45. If for some reason I delete that 2 plus, then it'll yell. It'll say, sorry, 43 is not equal to 45. Okay, does that make sense? If I make this 1 plus 1 plus 43, that's once again equal to 45. So all of this works out. Okay? Okay, great. So now once you have things like this, you can start writing functions with preconditions. So watch this. I'm going to write a function called assert. And the idea is that the assert function is supposed to take as input a Boolean value, but I want the Boolean value to always be true. Okay. So what I'm going to say is I'm writing above it the signature. So notice this is the plain Rust signature, and above it I'm writing this refined signature that says the assert function takes as input a boolean, but that boolean must always be true. So now I can start testing, and so all of this testing is happening at compile time. So I can say assert that 10 is less than 20, and so the compiler is essentially evaluating is 10 less than 20. It says, of course, 10 is less than 20. But if I change 10 to 100, then I'll get a little error, and it says, no, no, no. Over here, the assert function is only supposed to be called with inputs that are true. This does not evaluate to true. Okay, 100 less than 20 does not evaluate to true. So everyone is with me so far? Okay, let me just fix this so that I don't get the red thing, and it's back to 100 less than 200. Okay, so same thing over here. I'm just, we already
Ranjit,
saw this here. Yes,
I have a
yes,
question here.
yeah,
Please.
go ahead.
How do we know that the signature which we have um, feed it to the flux checker is the same? Like we did not specify, we only wrote FN.
Oh, how do we know that? How does it know that this one is connected to this one? You mean?
Yeah, yeah, exactly.
It's because so this is a thing that the Rust compiler exposes, where essentially I'm defining an attribute, and because I put it right above this 5, it attaches it to that particular function. So if I took this exact signature and I popped it over here, for example, let me do that. Suppose I copy this and I paste it over here. Now all kinds of weird things would happen. It would say, no, 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 this function does not return a usize. So it's just yelling. Okay, so it's literally because I put it right next to it over there. That's why. Okay, so this is just a thing that the Rust compiler allows me to do it. Attach extra metadata with the function 5 itself. Yep.
The carrier.
Okay, thanks, Ranjit.
Okay. Okay, great. So let me just return to the, okay, so that was quite straightforward, right? So here is, let me show you a slightly more interesting example that is not quite just numbers that are so boring. Um, Here's an example where, so what you can do is you can take the standard sort of vector API that Rust has, and you can refine it. So here what I've done is, so Rust has a data type for vectors, arrays, and what I'm doing is I'm defining a refined version of it, where I can take, just like we took integer I32 and I said it's indexed by 5, and I take booleans and I index it with true or false. I can take vectors and I can refine them by the size of that vector. Okay, so the number of elements that they have. And so I can start writing signatures that tell me how big a vector is, how many elements it has. So for example, I can say that the new method for vectors returns a vector whose length is equal to 0. Okay, so can you see this? It just says new, takes no inputs, and it just returns as output a vector whose length is equal to 0. And similarly, well, I'm going a little ahead of myself. Let's just look at this little piece of code, right? So here what I can do is I can write a function called vectest, and I can say vectest returns a vector of size 10. Why is that? Well, here's the code for vectest. I create this vector initially, which is of size 0, and then inside a loop, I have I equals to 0 while I is less than 10. I'm pushing the numbers, whatever, 1 through 10, and I keep incrementing I. And so at this point, the compiler is able to tell me that the size of the vector is in fact 10. So watch, if I change 10 to, if I change 10 to, for example, 100, then I'll get lots of errors. First of all, this assertion is no longer true, right? Because I may be greater than 100. So let me just say, don't worry about that. But this will still be an error, right? Because the size of this vector is going to be 100. Okay, so let me not break my code. Let me just keep it back like so, and continue thus. Okay. Okay, so let's keep going with this. So next, what I'm going to do is, it's fine to just have hardwired constants like 0, 5, and 10, but it's more interesting to start having functions where these indices can themselves be parameters. Okay, so for example, I want to write a signature that says, I imagine I want to write a function that takes as input a number, an I32, and returns true or false, and it's true exactly when that number n was positive. Okay, so what I'm going to do is I'm going to let you write a signature that looks like this. A function that takes n, which is an I32, and it returns as output a boolean. And now notice this index expression can refer to this parameter n. Okay, so I'm going to say it's a boolean such that n is greater than 0. Okay, so this expression is going to be true or false depending on whatever the value of n is, right? If n is 100, this is going to be true. If n is negative 5, this is going to be false. And so I want this function, so this function is now saying it returns true or false depending on whatever that n was. So let's look at some examples. So where did I have is pos? Here we go. Okay, so look at this. I'm writing function is pos, takes as input n, which is at I32, and returns a boolean, which is n greater than 0. And what shall I do? Let me just check. So let's just test. Let's write a function that tests is pos, right? So I'll say test is pos, and maybe I'll check something. Well, okay, Copilot is very helpful. Wow, check it out. This is I swear I did not pay them money. Here we go. Let's try this one by one. So assert is pos of 10. So that should return true, and it does return true. Suppose I try assert is pos of negative 10. That should of course be a failure because this pos of negative 10 is false. And in this case, if I put a not there, then again that condition becomes true. Okay. Hopefully people are so far with me. But let's look at a slightly more interesting example, which is the length method. Okay, so if I look at the same, so remember this, the method new. So this returned a vector of size 0. A more interesting method would be length, which takes a vector of some size n and returns as output a u size, which is basically Rust unsigned int, right? Which is exactly equal to n. So whatever vector you give it, it's going to give you back as output a number which is exactly equal to the size of that vector. That's what that's what this is going to do. Okay, so let's look at some more examples. So suppose I have an example here of an increment. Oops, wrong function. Fn inc, wrong thing. Let me pop up a second. Oh gosh, well that's a bit strange. Where did all my, oh gosh. Okay, I'll just write it somewhere here. So here, let's try this. So I can write a function called increment. Okay, function, let's just call it inc, which maybe takes x as I32 and returns at I32, x plus 1. But I might give it a signature. Oh, check it out. Copilot is pretty good at that as well, it seems. So it takes as input x, which is an I32, and returns as output an I32, which is equal to x plus 1. So notice we're being a little fast and loose with integer overflow here, but that's just for this for the purposes of this demo, right? So okay, so inc, I can check that, and now I can check, for example, that is pos of, sorry, never mind, is pos. Suppose I want to check that increment of 10 is equal to 11. Okay, that's a reasonable thing to check. Let's just get the parentheses right. What is it complaining about? Closing delimiter something something. Oh, there's an extra parenthesis there. That's what it's yelling about. Let's fix that. Inc 10. What is it not? Oh, did I have an extra? Okay, let's just call it my ink because I probably have some other definition somewhere that it's yelling about. My ink, I'm going to call this my ink. There we go. So my ink 10 is equal to 11. If I change this to 12, it's going to yell and say, sorry, that is not equal to 12. Okay. Okay, so let's press on. So in all of these cases, I assume that to know exactly what the value of the particular thing is, right? So it's an int32 that is equal to n, or int32 that is equal to 5 or 12 or 42 or whatever. Often we don't know exactly what the expression is. We don't know what the exact value is, but we know that some condition is true about it. Okay. So this brings us to the second kind of basic type that you can write, which looks like this. It's called an existential type. It's a fancy word, but what it says is you have a base type like int or bool or whatever, and the actual value is some value v such that some predicate of v holds. Okay, so let's look at some concrete examples. For example, to define a set of non-negative ints, I might say you have an I32, which is in any old 32-bit int, but I have this extra constraint that says I32 set of values v such that value is greater than or equal to 0. Okay, and so this is going to define the set of non-negative I32 values. Okay, so no negative values would be allowed, only non-negative ones. Let's look at some examples. So for example, if I have, here's a function called abs, and it takes as input x, which is an I32, and it returns as output. So what does it do? It checks if x is less than 0, in which case it returns negative x, else it returns x, right? And so there's an absolute value function. And so what I can guarantee is that if this function takes x as input, then the output is going to be some value that is greater than or equal to 0. Okay, that's non-negative. And in fact, I can probably guarantee something slightly nicer. I can probably say, if you think about it, that the value is in fact greater than or equal to x. Okay, if you sort of think about it, because I'm in either case, I either return x, which is greater than or equal to x, or x is negative, in which case I make it positive and it's going to be greater than or equal to x. Okay. Um, so you can take these kinds of types, and it's often convenient to name them. So for example, I might define a type for positive numbers. I might say type pos is equal to u size v such that v is strictly greater than 0. And then I might write things like this. So here's a floating point division function, right? Takes x, which is an f32, y, which has to be positive, so not 0, it has to be strictly positive. Notice that this assertion passes. This assertion passes because input is a pos, right? If I change this pos and I say it's a u size, then of course the assertion won't pass, because it could be that u size is any unsigned integer, which could be 0, and so that assertion is going to fail, and I might do a division by 0. And so instead, oh, go away. If I replace this and I make it pos, then that particular assertion is going to pass. Okay. So far, does that make sense? Okay. Um, Another fun sort of example of a thing where we use these sort of existential types is the signature for the get method for vectors. So let me pop back over here to my vector library. So remember, we had length, which returns the size of the vector. You can write various things. So here's an isEmpty method, for example, that takes a vector whose size is n, and it returns a boolean which is true if that n is exactly equal to 0 and false otherwise. Let's look at the get method. So here, what I want is that my get method be such that whenever I pass in, so what does a get do? It takes a vector as input, and it takes an index at which you want to read that vector, right? I want to get the vector at position I. I want to make sure that that index I is always going to be at most the size of the vector. So if the vector had 10 elements, then the index must be between 0 and 9 inclusive. Okay, you can't have 10 because that would be an overflow. And in the case of Rust, they do have some sort of array overflow checking, but you can sort of disable that when when you sort of compile for what is called release, for a release build, in order to make things fast. And so here what we want to do is just make sure that compile time, that whenever you have an array lookup, it's not going to fail. Okay, so imagine I can write this as my signature for get, and the moment I do that, here's what happens. Let's look at this. So here's a function that is supposed to compute the Euclidean distance between 2 points, and now the type checker is going to start yelling. So let's look at this. So distance, it takes, so we'll talk about and in a second, but for now just think of it as a pointer to a vector of float 32s. F32 is a 32-bit float. It takes x and y are two vectors of 32-bit floats, and what I want to do is to compute the Euclidean distance. So I'm just writing a little loop, right? So I say initially the result is 0, 0.0, and then I'm looping from I goes from 0 to the length of the first vector. Okay, and in each case I'm computing d of I. Delta I is xi minus yi, and then I'm adding di times di, the square, right, to this result, and I'm incrementing I and I'm returning res. Okay, so this is essentially computing. If I wrote it out, what would this be? I guess this is, oh, well, there you go, fantastic. It's computing something like that, except that I haven't computed I'm not taking the square root. Okay. Fantastic. Oh, look at this. Copilot is telling you that x and y should be vectors of length n. And so we want to specify. So right now, the type checker is yelling, well, my friend, you have y of I, but maybe y doesn't have n elements in it. And so maybe the index I is out of bounds for y. And so what we want to do is we want to tell the type checker, no, 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 don't worry. When I call you with x and y, I promise to call you with two vectors that have exactly the same size. And so I'm going to do that like so. Okay, so I write is a function where x is a vector of float 32s of size n, and y has exactly that same size n. And the moment we do that and I hit save, now that particular red thing is going to go away. Okay, so is everyone with me so far? Okay, I'm taking these. The way I specify that that when you look up a vector at position I, is going to call that get method, and in that get method I specified that the index I must be between 0 and the length of this y. And if I didn't specify that the vector y has the same dimensionality as the vector x, then I got a type error. Okay, fantastic. Okay, let's press on. Okay, so next let's see how this type checking works when you have pointers. Because when you have languages like Rust or Java, one of the hard things is, well, what happens when you have multiple people that can have locations, can have pointers, and can update things. Okay, so here's what happens. Um, the idea is, like, this would really help to have some animations, but I'm too scared to go full screen. Uh, what? So unlike a regular type checker, in a regular type checker, when you say whatever, you said let x is equal to some expression, we compute the type for x for once and for all, right? However, in the case of these refined types, that's not good enough. What you really want to do is, as the location or as the variable is getting updated, you want to change its types. So let me just show you a very concrete example. Okay, so consider this. Suppose I have, so what is in Rust, by default every variable is not updatable. Okay, so you just, if it's like in JavaScript or where you say const. Okay, so if I say let x equal 0, then Rust is already going to complain and say, hey, you said let x equal 0, that means x is immutable, you're not supposed to change it, so you can't do x plus equals 10. Okay, so if you really want to increment it, you have to say, okay, don't get so mad. Please, I'm going to declare it to be a mutable variable. Okay, so when you do that, the Flux says, oh, okay, I see you took a mutable variable and you initialized it with 0, and so the type of x at this point is I32 with the value 0. Okay, so we can prove that x is in fact equal to 0. That's why this assertion passes. Now, when I say x plus equals 10, the type checker is updating the type of x. Okay, it knows that at this point the type of x is in fact 0 plus 10, the old type plus 10, so I32 of 10. At this point, it's updated it further, so we can prove this assertion is true. When I add the plus 20, this 10 has now become 30, right? When I add another 30, this has become 60. And so finally, when I return this, I can prove to you that, let's see, Flux, oops, sorry, what was it? I'll just let it autocomplete, that this result is in fact 60. Suppose I mess this up and I make this, I don't know, 600 or 6,000, then it's going to yell and say, no, it's not 6,000. I can't prove to you that it's equal to 6,000 because in fact the only thing it is equal to is 60. And so if I edit this, fine. Suppose I leave it as 6,000, it's going to yell. Um, can somebody tell me how can I change? Let me just throw this open to somebody who's in the audience. Can you tell me how can I change the code to make this red thing go away? So it says I cannot prove that the output is equal to 6,000. So how can I change this code so that the red thing goes away? Would anybody like to take a guess? How can I change this so that it gets changed so that in fact it is, yeah. Anyone? I don't know, Saurav, if you can see, yes. I see somebody saying something, if you can just relay it from the back.
I'm sorry, we were muted.
Oh,
It should be
yeah.
better now.
Yes,
Yeah.
I can hear you now. You were. So any, yeah, what should I do? Imagine I am a keyboard. How shall I change my code here? I don't want to, I just want to change stuff in these gray lines. I can add stuff, I can delete stuff. What should I do?
I mean, you make x equal to 6,000. I don't see why that should be a problem. Like your post condition
Oh.
requires to be 6,000, right?
Oh, so you're saying, cool, just do this. Equals 6,000. I confess I had not thought of that, but that will certainly work.
Why would that not work?
Oh, now Rust is complaining value assigned to red is the x is never red. Okay, fine. We'll use that value. Suppose I just add, what is the difference between 60 and 6,000? Like 5,940, I think, is perhaps what I need to add, right, to get it up to 6,000. Okay, there you go. Okay, fantastic.
What
Okay,
would that-
that was pretty easy, right? Okay, let's look at a slightly more, sorry, was there a question?
Yeah, is that not what you expected? Because like you either relax the post condition or you make or you satisfy it, right? Is that
Exactly.
not-
You either, exactly so. So in this case, I wanted to just say you are not allowed to relax the post condition. So
Okay.
somehow I just want to force you to, respect the post condition. I think it probably works if I multiply by 100, but let's see what happens. Okay, yes. Okay, 60 times 100. Yes, that's all I was trying to illustrate, right?
Yeah, sure.
So let's look at a different function. Okay, so here, um, here's a function, whoops, sorry, called min index, and the idea of this function is I want to loop. So I'm given a vector again of 32-bit floats, and what I want to do is I want to loop over this vector, and I want to return the smallest index. So the position in this vector, here, I don't know why I have all this stuff over here, right? I want to return the position in this vector whose value is the smallest. Okay, and so what should happen is that if I give you this vector, then the output, suppose this, so let's try and write a specification for it. I'm going to disable this copilot because it's a little too clever sometimes. Disable completions. Okay, let's not cheat. Okay, good. So Flux, let's do it the old-fashioned way. So I'm going to write this. So fun. Wait, I thought I disabled it. Apparently not. It is harder to disable it than I thought. Okay, but this is in fact what I was going to type. So let me write it down. So suppose I write this. So let's look at it. What it says is this function takes as input a vector whose size, a pointer to a vector to be precise, of length n, and it returns as output an index which should be a value that is strictly between 0 and n. So 0 because it's usize unsigned, so it's non-negative, and less than n. Okay. So let me hit save and see what happens. It says the post condition cannot be proved. Can somebody tell me what is the problem? If I give you a vector between 0 and n, sorry, of size n, surely, and I'm running this loop, surely the output should be a number that is, at most n. How can I produce an index that is larger than n? Can someone guess what's going on over here? So it says, sorry, you're returning. So I mean, the loop, there's nothing funny in this loop, right? I'm defining a variable min, the whatever I believe the current the minimum is, initializing it to 0, and then I'm just looping while I is less than, less than the size. If the current value at I is less than my whatever my candidate is minimum, then update the minimum to be I, and increment the counter I. So it's just very classic sort of imperative loop. What is going on here? Can anyone spot the bug?
N equals 0, I guess.
Yes. So if the array is empty, then what happens? If the array is empty, so if the length is 0, then we just return 0, right? We would never go into the loop. We would just like bounce out and return 0. And there's no guarantee that 0 is strictly less than 0. In fact, 0 is not strictly less than 0. So how can we fix this code? So whoever that gentleman was last time, in this case, do we want to fix the code or do we want to fix the spec? What should we do here? Maybe if we're computing a minimum index, the only sensible thing is to require that the array is not empty, right? So can you tell me how would I edit this to specify that the input array should not be empty?
Assert statement with what?
Like to verify that the length is not equal to 0.
Okay. Okay. So the idea is assert that it's
Okay.
not 0. N is
Okay,
not
so
0.
let's just say a dot. Okay, that's cool, and then assert. Okay, great, fantastic. Well, now it's just going to say that the assertion fails because it's like, well, I have no information to say that this assertion that the size is non-zero, right? So somehow I want to promise that this function itself will not be called with things that are not equal to 0, right? With arrays that are non-zero. So how can you tell me what would I edit in the spec? Here's the spec.
Yeah. So we can modify the precondition to say that n always has to be greater than 0.
Exactly. So what I'm going to do is here I'm going to say A is not any random A, but it's all that stuff that you said, and n must be greater than 0. Okay. So now when I do that, this assertion is also going to pass, and of course the output is going to be less than n, right? Okay. So far so good. Okay, great. Let's press on. Okay. Fantastic. Okay, so far we didn't really have any sharing, and we weren't really using references in any interesting way. So next, let's see what happens when you have what Rust calls borrowed references. So borrowed references in Rust is, for those who are not familiar with the language, is roughly Rust distinguishes between read-only references and references through which you can write. And the reason it distinguishes between these two is because the Rust type checker makes sure that if you have read-only references, then it's fine. You can have as many read-only references as you like. at any point in time that are live, because multiple people could be reading a thing with that doesn't change the value. But if there's a write, if there's a reference that can actually write to a value, then there's exactly one that's ever live at any point in time. Okay, so turns out to be a very handy thing for this kind of type-based verification. So let's look at this. Okay, so here's a function. I'm just actually, let's go back over here, right? It's called test, and what I'm doing over here is I'm saying test is a function that takes some x. X is a read-only reference to an i32, a 32-bit integer, but it's a read-only reference to a cell where I'm guaranteeing that the cell is always non-negative. Okay, so the contents of the cell are non-negative. So here, if I say let n is equal to star x, which is kind of like in C, if I have a reference, star is the value of the thing that is pointing at, right? Then n is going to be greater than or equal to 0, because I said that's what I said in the type. So let's go back to my editor buffer and let's try it out. Oh, that's not what I was looking at all. Where is my, okay, fine, I'll just write it. Here's my silly test. Okay, simple test, fn simple test. Okay, so x is no, that was not the test I had in mind, my friend. Okay, i32, right? And here I'm just going to say let n is equal to star x. Okay, and then I want to, okay, assert that n is greater than 0. Fine. Okay, n is greater than 0. And now I can write this signature that says flux sig. No, that's not what I had in mind at all. V such that V is greater than or equal to 0. What is this ensures business that it keeps coming up with? Let me just close the parentheses, close this, and there we go. Okay. So notice this passes. Of course, if I change this to n greater than 10, it's not going to be true because there's nothing in this input type that says that the thing it refers to is greater than 10. Of course, if I further change this to equal to 10 or even 100, then the assertion will pass because, of course, the contents are greater than 10, right? Okay, fantastic. Let's move on. However, you have to be a little careful when you have this kind of mutable borrow. Okay, so this and mute is the thing that Rust has that says where it says you can now actually update the contents of the reference. Okay, so for example, let's go and look at this guy. I can write a function called, here is this, this is not what I had. Okay, so I'm just going to duplicate this. Okay, I'm going to call this a second function. Let's just call it adder or something. X takes an and mute. Actually, let's see if suppose I didn't do that. Just to show you what happens. If I say star x plus equals 1, and then I do something like this, notice that Rust will complain. It'll say, hey, you can't assign to star x. Actually, you can't you can't update x because it's behind an and reference. Okay, and so I would have to change that and make it an and mute, which now allows Rust to increment it. But now Flux is going to yell and say, hey, I don't know that n is greater than 10. Okay, there's no information that you have that tells me it's greater than 10. And so naturally, I would have to specify that. I might say something like greater than 100, and now everything is fine. Okay, but now let me try this. Suppose I change this code from plus equals 1 to minus equals 1. Okay, so I'm decrementing this. Does it make sense? Okay, let's see what happens. Ooh, you get an error. It says assignment might be unsafe. And the reason it says that, can anyone speculate? Why does it say that? Why was it okay? Why is this okay? But why is this not okay? Let's just comment all this other stuff out. Can anyone speculate? Like, why is it that the first one is okay, but the second one is not okay?
If the value is 10, then the post condition might fail because it'll end up being 9.
Exactly. So here it's not even a post condition, right? So the thing is, when I say that I'm an i32 and I'm greater than 10, I'm basically telling the type checker that no matter what, when you update the contents of this cell, you must preserve this fact that the value is greater than 10. So I can add 1, I can add 10, I can add 100, I can add whatever I like. But the moment I try to decrement, all bets are off because I might break the property of that cell. Okay, so that's why it sort of yells over here, and I don't let you change that particular type. Okay. Now this is a little too restrictive Because of course, if you have read-only, if you have these mutable pointers, you do want to update their contents. Okay, so for example, you might do. Here's another little example. Let me show you this. Okay, so let's look at where did my little decrement function go. Here's decrement. Okay, so check this out, right? So imagine I want to write a function. Did I define a type called pos? I did define a type called pos, right? Suppose I make this pos. So now it complains and it says um, assignment might be unsafe. Can somebody tell me how would I fix this? So remember, pos is supposed to be the set of all the, here's the definition of pos, right? Value must be strictly greater than 0. So can someone tell me, is there a way we can change the branch condition so that this assignment would be safe? Remember, I have to preserve the property that no matter what, x is always strictly positive. So here I am, what would happen if n is 1? If n is 1, then I have n minus 1 and x becomes 0, right? So what can I change to make this property true? To make this error go away?
Greater than 1.
Exactly. I can just tweak this so I make that greater than 1, and then it's the type checker is quite happy. Okay? Okay, fantastic. So I showed you this sort of increment and decrement, and I showed you actually get and set already, right? And I also believe I showed you, so this is the method that we were using. Let me show you the set method. So just like you have a get, the function that you use to update the contents of an array, that takes a mutable pointer to the vector. Okay, so it takes a and mute to the vector, and it takes an index, and it takes the new value that you want to write into that cell, and then it updates self.inner whatever to that new value, right? And just like in the get method, I require that the index that you pass in must be a valid index. Okay, so I'm just making sure that the index is valid, and this is why we got that error previously. Whoops, where's that function that was? Oh gosh, I think it was called add. Was it not called? No, this is the wrong. No wonder I'm in the wrong window. This was the function, not min index. Where's the one with the two values x? Distance. No, actually, let's just. Why am I doing this? Sorry, I'm just trying to find the little demo. Oh, here we go. Plus, it was right there. Okay, so let's look at this. So here's a function called plus. It takes these two vectors, and what it does is, again, the two vectors have the same dimensions, and the idea is I'm taking the contents of y and I'm incrementing pointwise x of I with xi plus yi, right? I'm bumping it up, and of course, I'm iterating and doing it for every one of those cells, right? And so it all works out, but the reason it works out is because I specify that the index, the dimensions of y are the same as that of x. If they have different dimensions, then again, that this is going to be an out of bounds, a possible out of bounds exception, and so the compiler is going to yell. Okay. Okay. Very good. Now, sometimes the last sort of language feature that I'll show you is where you actually want to change, just like remember when I said let mute x equals 10, and then I incremented x, and then I incremented again on, we got 6,000. Sometimes you want to do that with pointers too. It turns out it's surprisingly rare, but sometimes you want to do that as well. And for example, this is frustrating. So suppose I have this increment method. Where was my, here's, no, not that one. Here's my add method. Okay, so let's look at this, right? So imagine I have this adder. I have an x as an and mute, and it increments x. So I would like to be able to prove something like this. Let's just have my test adder again, whatever test adder something, right? So here we go, right? So I would like to say initialize x to the value 10, take a reference to x, and pass it to adder, and so adder should increment the value of that pointer. And so at this point, I should be able to prove that x is equal to 11. Right? However, we cannot prove that. And the reason we cannot prove that is that the adder method just says, hey, you give me a pointer that is non-negative, and that's the only thing I know about it. That when the function finishes, the only piece of information you have is that the result is non-negative. So this is a bit annoying, right? So I can prove that x is greater than 0. Sorry. I can prove that x is greater than or equal to 0, but I cannot prove that it is equal to 11. Okay, so I want to be able to prove things like this number is in fact equal to 11. Oops, sorry. But I cannot do so because this contract is too strong. And so what we instead allow you to do is to write a signature that looks like this. Okay, so this is the last sort of piece of machinery that I will introduce before we jump into the actual analysis. It looks like this. So instead of just taking a and mute, what I tell Flux is you can take what we call a strong reference. So a strong reference, this is sort of this name comes from some of the program analysis literature. But a strong reference means that something, it's a reference whose type you can change, or what is called you can strongly update. So here what I'm saying is this function takes x, and x is a strong reference to an integer who, when you begin, the value of that integer is n. But when you finish, so ensures means upon exiting the function, the same pointer x now points to an integer whose value equals n plus 1. Okay, so upon entry, the value was n, but upon exit, the value is n plus 1. And so now, if instead of calling adder over there, I change this to call my inc function, which is the thing defined below, now notice that I can actually prove that this assertion holds. Because now the type checker is clever enough to realize, aha, at this point, x was, oh, actually that's very good. It says that it knows that x is a pointer to some location in memory, and that location in memory has the type i32 at the exact value 10. But now when it comes back over here, it has figured out that x is still a pointer to that location in memory, but at this point, that location holds i32 with the index 11. And since it's at that index 11, I can now prove that this assertion holds, and of course this assertion always holds. Okay? And so this is a convenient function because it lets us write, it lets us, again, to go back to my vector API, it lets us write methods in this API that change the size of a vector. So for example, if you have a push or a pop method that add or remove elements from a vector, you might say that the push method takes as input the vector, and this vector is of size n, and it takes the next element, which is of type t. This is a polymorphic vector, and it ensures, so when you're done, upon exit, the size of that vector is now going to be n plus 1. So whatever the original n was, plus 1. Okay? And so if I come back to my little demo, let's go back and let's look at some examples, increment, blah, blah, blah. Here we go. Okay, so I'll just write a simple test first. So let's just write functions simple push test. Okay. And here what I'm going to do is I'll define a vector. Let me mute. Okay, that's not bad. But except that in Rust, well, we'll see. It'll probably yell at me for a second. And now suppose I say v dot push, let's just push the value 10. And I say v dot push, let's push the value 20. And I say v dot push, let's push the value 30. Okay. Oops, sorry. And now suppose I want to assert that v dot length is actually equal to 3. This is going to pass. So the type checker is happy with this. To make sure, just to convince you that the type checker is doing something, if I comment that line out, now it's going to yell and it's going to say, hey, I can't prove this assertion because of course it's not actually true, right? We only push 2 elements, so the size is equal to 2. Okay. So a slightly more interesting version of this simple push test is the following. So let's look at this guy. Okay, so what is this method doing? This is a method I'm calling it range, because it takes a low, a kind of a starting point, and a high, an upper point, and it's going to return a vector of numbers between low and high. Okay, so how does it do that? Well, it initializes I to low, it creates this vector, and then while I is less than high, it keeps pushing I and it increments I. Okay, so it's just going to start with I, then it'll push I plus 1, then I plus 2, then I plus 3, then I plus 4, da 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 da, until all the way it goes to high. Okay, and here what we can show is the following, that this vector, if you give it a low and a high, where the high should be greater than low, right? I mean, as long as you give it a high, that's fine. Greater than or equal to low. Maybe you want to return an empty vector. What you get as an output, let's look at this slowly because it's saying a lot of things. What it says is you get back a vector of elements where each of those elements is between low and high. So every element in this vector is between low and high. And furthermore, the size of the vector is high minus low. Okay, so if low was 0 and high was 10, then the vector will have 10 elements. If low was 5 and high was 10, then the vector will have 5 elements. Right? Does that make sense? And of course, all of this, well, we'll see in a second how this actually works. Okay, let me move on. I showed you all of this. Push, range, very good. Um, Let me just pause here and I'll show you a sort of a larger demo. Okay, so all of these were very small little examples. What I want to show you is a slightly larger demo that, let me check the time. Actually, Saurav, we have like 20 minutes left. Is that right?
That's right, Ranjit.
Or maybe 10 or 15. I wonder, maybe I should just stop with the demo and there's no way I can, well, we'll see how it goes. Maybe I'll skip the demo and I don't know. Let me just take a quick poll. Maybe Saurav, you can do a poll for me. In the next 15 minutes, shall I continue with demoing a more complicated example, or shall I jump to the analysis, to showing a little bit about the analysis? What do people what which would people like, or which would
Okay,
you
I'll
prefer?
take the poll. Yeah, sure.
Yeah.
Okay, most people are bending towards analysis, I guess.
Okay, very good. Let's switch over then to see how this actually works under the covers. Okay. La la la. Oh, how convenient. It was the very next slide. Okay, so how does all of this work? Okay. Maybe at this point, since I'm going to dare to try and go full screen. Let's hope for the best. Okay. So how does the type checker work under the covers? So here's the idea. At a very high level, it's a kind of type directed abstract interpretation, and I'll sort of explain this slowly. Okay. So the key idea is this. What the analysis has to figure out is at various points in the code, what the hell are the types of all the various expressions? And the key bit is the following, is that every time I have an unknown refinement type, I am going to do what my mother taught me how you do, what the point of algebra is. Whenever there's an unknown, you introduce a variable for that unknown, and then you can sort of come up with constraints on those variables, and you solve for those constraints, and that will tell you what the types are. So let's just see how this works. Okay, so what's going to happen is I'm going to write the code. The code is going to pass through this type checking. I'm writing it in quotations. And what the type checking is going to do is going to produce a system of what are called horn constraints. And I'll show you this by example in a second. And then I'm going to solve these horn constraints. And if my solver says, yes, you can solve them, then that's when you get this green check, which means there were no little red squigglies. And if the solver says, no, you can't prove those constraints, then that's what's going to give us the little red lines. Okay. So let's see how this analysis works for one example. The same minimum index, this, I think it was the range example, right? That I just showed you a second ago. So recall, here was the code. I have a function called range. It takes a low and a high. And I have this little loop that it spins around in this loop and it sort of keeps pushing. And I want to prove that the result is a vector of numbers between low and high. And the size of the vector is high minus low. So let's see now how this analysis sort of works. Okay. So first of all, notice that there's some sort of data structure collection stuff going on over here. Okay, there's two sort of slightly tricky things. One is we're creating collections and we're pushing values into those collections. So we're sort of updating the values in the collections. And let's see how the analysis works. Okay, so what it does is it sort of follows the plain type checker. So the Rust type checker says, okay, you said let mute I is equal to low. And so the type checker says I is going to be a U size. So one of these, what do you call it? Unsigned integers. And since we created a new vector, Rust will say, oh, it's a vector of U sizes. We don't know anything about the contents. We don't know how big or small it is. So what now Flux, or what the refinement type checker does, it says, aha, it's a U size such that some condition is true of that U size. There's some property that we're trying to solve for this I. And similarly, this result is a vector of things. Okay, it's a U size of, there's some property of those U sizes, which with what the first question mark represents. And the length of that vector is also something we probably want to say something about. So I'll introduce another question mark, right? And so these are the things we want to solve for in order to produce this output where at the result when we say res is returned, that the res is in fact has dimension high minus low and every element is between low and high. Okay, so here's the first idea is what I'm going to do is every place where I have an unknown refinement, so where I had the question mark, I'm going to introduce a variable. So this $ki stands for the unknown invariant about the variable program variable I. This $kval stands for the unknown invariant about the individual cells of the vector. And this klen v of I is the unknown invariant that holds about the size of this vector. Okay, and notice it's v comma I because this unknown invariant can be a predicate over the size itself, which is v, and I, because maybe it depends on the value of I. Okay, so it could be a binary or a three-way predicate, and so on. Okay, so I've introduced these three variables: $ki, $kval, and $klen, and I don't know I don't know what these sort of represent unknown refinements or unknown invariants. Next, what I'm going to do is I'm going to take the code, and I'm going to do this very fast. I'm just going to show you this by example. Okay, so I'm going to take this code, and I'm going to generate a system of constraints. And these constraints are going to relate, they're going to be logical constraints that relate ki and kval and klen with all the stuff that's happening in the code. So let's look at this both slowly and quickly. Okay. So here is, I just dumped out the constraints. Don't be alarmed. I will go through this slowly. Okay, so let's look at this one by one. So on the left, for some reason, I cannot point. I don't know why. This wretched software is not letting me point. So I'm just going to have to use I'm going to have to use my words. So on the left in green, notice that I have the preconditions that said low is U size and high is between low and high. And so notice on the right hand side in my logical constraints, I say for any low and for any high, which are integers, assuming that low is less than equal to high. So assuming, I see, because you see the little implies, so that arrow means implies. So low less than equals to high implies all the rest of the constraints. Okay, so now let's look at the rest of the constraints. So that's the precondition. Low is less than equal to high. Okay, so the first constraint comes from the yellow. So notice that the value of low is initialized to I. And so whatever my invariant was, whatever my property was for I, which is represented by this predicate, unknown predicate k of I, that predicate must be true for the value low. Okay, because low was the initial value of this index I, of this variable I, and so this invariant must be true for $ki. And so that's what that yellow thing is saying. $ki of low must be true. What else must be true? Well, let's see. So I initialize the vector. That's what this little orange or pink, I don't know how it's rendering in your thing. The line res equals rvec : new. So remember that new returns an empty vector whose length is 0. And so what that tells us is that the klen invariant must be true when the length is 0 and the current value of I is equal to low. Notice that on the previous line, we initialized I with the value low. So this predicate must be true for I and low. Next, let's move on to this pink bit. So now we're inside the loop. In the loop, we have the values of I and the size of the vector change, right? Because we're updating I and we're pushing to res, so we're updating the size of res and we're incrementing I, and so both of those change. However, ki and klen are invariants, so they are something that's going to be true no matter how many times you spin around the loop. And so what I can say is for any I and for any n, assuming that ki is true, so I say ki of I implies and klen of n comma I implies. So what do they imply? They imply that, now let's zoom into the body of the loop, res.push of I. So what that is saying is, and notice that the body of the loop is only executed when I is less than high. So that's why I have this little implication, I less than high implies. Okay, and what does it imply? It implies three things. First, it implies that $ki is true for I plus 1. Why? Because we're incrementing the value of I, and so that invariant must also be true for I plus 1. We're updating the size of the array, res.push of I. So now the length becomes whatever the old length was plus 1, so n plus 1, and I is also incremented to n plus 1. So whatever this length relationship is, it must be true now for the pair of n plus 1 comma I plus 1. And finally, I'm pushing the value I into the array itself. So the array cells, whatever invariant they have, this $kval, that must be true of the integer I. So that's what $kval of I is saying. Okay. And finally, when you break out of the loop, which is the light blue thing, which is just res in the code, that's going to give us three constraints. Whoops, sorry. Oh no. Oh, sorry. That's going to give us, the three sort of things down in blue, which look like, oh gosh, sorry, I went too fast. I'll do this very slowly this time. Okay, no more presses, Jhala. Here we go. Okay, fantastic. So notice when we come out of res, it's going to say not of high I less than I, because you break out. If I is less than high, you continue in the loop, otherwise you break out. And so the analysis knows that it's okay, not of I less than I. In that condition, n must be equal to high minus low. Why? Because that's the post condition. We want to prove that the output of the output length of the vector is equal to high minus low. And finally, we want to prove that every element of the array $kval of v is such that that v is between low and high, right? So that's coming from the blue post condition up at the top. Okay, so now what the type checker does, I sort of wave my hands very fast. There's sort of, I can point you to the various papers that describe how this happens, but you can sort of take my word for it. The type checker sort of walks over the code and it produces this set of constraints on the left. So you have these kind of $ki, $klen, and you have these little implications between them. And so now what we have to do is to somehow figure out, well, how can we solve out kval, ki, and klen such that all of these constraints are in fact true? Saurav, how much time do I have left?
15 minutes.
15 minutes. Okay, very good. Then I can perhaps explain briefly how this solving works. Okay, so the problem we're left with is how do I solve out for ki, klen, and kval? Okay, so let me briefly outline what this procedure is. It's not very clever. It's quite straightforward. Here's the idea. Okay, so remember that ki, kval, klen, they represent some unknown predicates. And so what I want to do is I want to synthesize those predicates somehow. And so the first step, I'm going to walk over my constraints and I'll just pull out little fragments from which I can synthesize those predicates that I can combine to produce a solution. Then in the second step, I'm going to create an initial assignment for the ki, kval, and klen. And then in the third step, what I'm going to do is I'm going to keep throwing out things that can't possibly be true until I'm left with the only thing that could possibly be the solution. Okay, so there's a kind of three-step procedure. Okay, so how do I find these candidate, I call them qualifiers, which are just predicate fragments. What am I going to do? Well, I'm just going to look at the constraints and I look at the little fragments that appear inside it. Oh, there was a thing low less than high, so I shall make up fragments like star less than v and v less than star. Okay, it's very syntactic. Oh, I less than high, I will make up star less than v, v less than star. Okay, strictly less than. And similarly, I saw a thing down there, n equals high minus low. So I'll just make up a thing, v equals star minus star. So all I'm doing is I'm taking the little atomic fragments that appear in my constraints and I'm replacing the variables with stars. That's what's happening. Okay, where star means you'll see what star means in just a second. Okay, so those were my candidate, I'm going to call them qualifiers. Now in my second step, I'm going to create an initial assignment for ky, kval, and klen. Okay, so what is this initial assignment? What it's going to do is I'm going to take each of those candidates, right, the little rainbows, fellows that I have up at the top, and I'm going to replace each of the stars with the variables that are in scope in the constraint. What do I mean? Let me just show you as an example. So I'm going to say, okay, let's just say kval of v is this entire vector of candidates. Low less than v, high less than v, v less than low, v less than high, etc., etc., etc. Okay, I've taken each of those, I've taken the purple thing up at the top, and I've just plugged in for star low, and I plugged in for star high. I've taken the blue thing, I plug in low, I plug in high. I take the green thing, I plug in low, I plug in high, and so on. That's all I've done, right? There's nothing clever here. Okay, I'm just brute force blowing all this out, and I'm getting all these candidates. Okay, so step one, generate these candidate qualifiers. Step two, create this initial assignment. Now the heavy work is done in step three, where I'm going to take all my candidates that I have in my initial assignment, and I'm going to whittle it down until by throwing out all the things that couldn't possibly be true. Okay, and this procedure is called computing a fixed point. So for those of you who know a little bit about data flow analysis, I'm basically going to do a data flow analysis, except it's going to use an SMT solver, decision procedure, to determine whether these facts can be true or whether they're bogus and need to be thrown out. Okay, so the intuition is the following. If for those of you who are Sherlock Holmes fans, you probably know this famous quote, which is, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. And so we're going to take this adage of Sherlock Holmes and sort of turn it into an algorithm, like so. Okay, so what I'm going to do is I'm going to now iteratively just pick constraints one by one, and I'll test out all my candidates in the assignment, and the ones that don't hold up, where it's not possible for that thing to be true, I'll just throw them out. Let me illustrate. So in the first iteration, I'm going to pick that sub constraint. Okay, so let me write it down over here. It says for all low and high, low less than or equal to high implies that ki of low, right? I've just zoomed in in this pane over here, ki of low. So now what I'm going to do is I'm going to take all my candidates for ki and I'm going to plug them in. Except for v, I'll plug in low. I'll literally substitute v for low. So I'll plug in all the candidates. These are all my candidates. Notice my current scoreboard is up at the top. I'll take those are my candidates. And now one by one, I will test if these facts can possibly be true. So how will I test that? I'm going to query an SMT solver. For now, you can just think of it as a decision procedure. It's doing some linear programming. Let's just say there's a black box that can answer these questions for me. For all low and high, does low less than or equal to high imply that low is less than or equal to low? And of course, the SMT solver will say yes, low is less than or equal to low because anything is less than or equal to itself. So I'm going to write a little check mark. So that candidate still lives to fight another day. However, when I try to test the next candidate, is high less than low, the SMT solver will say no. Just because low is less than or equal to high does not mean high is less than or equal to low. And so at this point, I will delete that candidate up at the top from my assignment. Okay, I hope that flame was bright enough to see wherever you're sitting on the other side of the planet. Okay, so we're going to delete that. Again, we're going to get a candidate low less than or equal to low. Yes, the SMT solver says that's always true, so that one lives. How about low less than or equal to high? SMT solver says yes, you assume low less than or equal to high on the left hand side of the implication. So of course you can imply low less than or equal to high. That gets to fight. But then when we come to the candidate low strictly less than low, the SMT solver will say no, of course not true, and it'll nuke that candidate. Similarly for the next one, high less than low, it'll say no, that's not true, it'll nuke that one. And so on and so forth, right? Low less than low, it'll nuke that one. Etc. etc. Low less than equal to high, no. Notice this is strictly less than, it'll delete that. Finally, you ask it, hey, how about low equals I minus 2? It'll say absolutely not. Why would you think so? And it'll just delete that other one, and so on, right? So all of those just get wiped out. And so notice we started with like, I don't know, 10 or 15, I don't know how many there were, and we're down to just 3 over there. Okay, and we're going to keep doing this. You just keep doing this. Now let's pick the next one. I get this k length. I'm just zooming in over here, and now I'm going to eliminate the candidates for klen. Okay, so again, I just take all the current candidates, and I'll query my SMT solver, and the SMT solver will say delete. That one also gets deleted. 0 less than equal to low, that also gets deleted, right? None of these facts are true because these implications do not hold. Delete, delete, delete. But notice the last two facts are true because 0 is equal to low minus low, right? Because low minus low is equal to 0. And so now we're left with exactly those two guys standing for klen. Okay, we keep going. I just zoom in down there, I pick k of I, and so on and so forth, right? At this point, notice that my constraint, I have to make some assumptions about ki of I and klen of n minus I because they appear up in my constraints up on the left. Rats, I can't point to my screen. And so we'll just take our current knowledge in our current assignment for ki and klen and plug them in over there. And again, we'll just query the SMT solver with the 3 remaining candidates. And this time the SMT solver is going to say the first one lives, the second one dies, and the third one lives. And so we're going to be left with exactly those 2. And so on, right? So there's the 4th iteration. I'll skip that for you because it's going to whittle away. Of the 2 candidates for klen, only 1 will remain. The second one will get killed. Okay. And finally, there's this kval. Same thing. I'm just going to plug in ki and klen and eliminate all the candidates that are not implied for kval by the SMT solver. And this time, as you might imagine, pretty much those 3 candidates live. All the other ones get turned up, cannot be proven by the SMT solver. And so at this point, we have essentially walked through all the constraints, and no matter which constraint you pick, no more candidates can be deleted. Okay, so all the other candidates remain standing. And so at this point, we have found a solution. Okay, so I found the solution. Kval is equal to low, blah, blah, blah. Ki is equal to such and such. And if I plug these things in, the constraints on the left are all satisfied. All of these implications work out. And so we sort of declare that this program is correct. Okay, so that's how the type checker says it's okay. So this, I should point out, this is, this particular algorithm comes in, it's been sort of rediscovered multiple times. So, it's in the late 90s, it's a form of what is called predicate abstraction. And then Leno and Flanagan sort of rediscovered it as something called the Houdini algorithm. And every 5 or 10 years, it sort of gets rediscovered, right, in a slightly different context. But really, this is a very standard fixed point computation that involves an SMT solver. Now, there was this whole segment here about how, this procedure that I showed you works not only for things like, when you have collections like vectors and data structures and so on, but also for higher order functions and closures, which are quite widely used in Rust and Java. But in the interest of time, I will skip over all of that. Uh, do I have like 5 minutes, sort of, or shall I stop right now?
Sure, Ranjit. Just want to leave some time for quick Q&A,
Okay.
but yeah, we can, if there's something, yeah, results, sure. I mean, please.
I'll just very briefly tell you where there was some. So we implemented this, and the results briefly are this: is that you can sort of compare this sort of typey verification with the closest sort of relative is what is called Floyd-Horst style verification, where you have to write down explicit pre and post conditions and loop invariants. And this whole algorithm that I just showed you where we were deleting stuff, if you look at the same example, it turns out that, with these other tools which are based on Floyd, or you have to do a lot more work because the programmer has to write all these somewhat unpleasant loop invariants that tell you various things about the program state at various points, which makes them not so much fun to use. Whereas in context, I mean, in contrast with the types, you don't have to write all of that stuff, right? So here I'm literally showing you the diff. The code is identical, but here's all this extra green stuff that you have to write when you want to do it in the classical sort of Floyd or program logic style, which the type style simply gets rid of because this algorithm that I showed you, the Sherlock Holmes algorithm, sort of solves all of that stuff out for you. So, um, and we sort of evaluated this on some bunch of benchmarks, and it turns out, the loop invariants can get quite substantial. So it's convenient that, you don't have to write them down. And perhaps what's even nicer is if you go back and look at some of these loop invariants, you'll see there's a bunch of these for alls. So you see these pesky little for alls. This for all here is saying every element in the array, for all k, if k is between 0 and the length of the array, then the value of the cell array at the position k is between low and less than high, right? So it turns out these for alls are actually not so much fun for the SMT solver. So it turns out they really slow things down quite a bit. In addition to slowing things down for the programmer, they also make the actual solving much slower. And so Flux, which is the type checker that I described, uh, tends to check these benchmarks a lot faster than with the classic Floyd-Horst style. So let me just stop here. I gave you this very high-level description of programmer-aided analysis. The way I want this to happen is by having the programmer write refinements, which give you these pre and post conditions, but they tuck them inside the types, and it sort of enables a type-directed abstract interpretation um, that allows you to sort of very quickly check programs and without a lot of programmer overhead. So you can sort of check it out, and let me stop here and take some questions. Thank you, Saurav, and thank you everyone for your patience with the technical difficulties.
Thank you, Ranjit. Thank you for the nice talk. So questions, either people sitting here or people online. Yes, question. Yeah. If you have a question, you may want to line up behind him as well, please. Yeah.
Yeah, I just wanted to say this is an amazing thing you have built. Like instead of catching errors at runtime, we can catch errors. Like we can just verify simply while writing the code itself. And Rust is definitely more type safe and memory safe. But can we build the same sort of thing for other languages like C or C++, or have they already been built?
Oh, can we build it first? The short answer is I spent like the reason my hair is so white is because I spent so many years trying to think about how to build these things for C and C++. The real answer is this. You can build these things for C and C++, but the trouble is aliasing. In C and C++, pointers can point at anything, and multiple things can point at the same thing. And when you have that, notice how, this nice thing where I say X is a pointer to a positive number. If I have some other random pointer Y that can go and change the value of that cell, then how do I know that X is still pointing at a positive number, right? All bets are off. So what you have to do is essentially, before you can start building the sort of fancy checker, you have to build some non-aliasing. So you have to build some kind of alias analysis on top of C, which gets really, really hard. In Rust, that problem is solved. So all the stuff we had to do in C and C++ that made it kind of painful to write, to use the similar system in C and C++, all of those are just solved in Rust because the Rust type checker just does it for you. So as one of my one of my favorite quotes is this, one of my colleagues, Simon Peyton Jones, says, in computer science or probably in life, Whenever people say something is for free, it means that you've already paid for it. That's what it means to say something is for free, right? So in a sense, in Rust, you get this aliasing for free because the Rust type checker is already forcing you to kind of have this very tight discipline on your pointers. So to answer your question, yes, you can do it for C. In fact, a much earlier version of the system I just described to you was done for C, like a paper I wrote like 10 years ago. But it's not nearly so nice to use because of C, I guess, is the short answer. Yeah.
Yeah, I just wanted to ask, is this in its like alpha phase or is it like being used by Rust developers right now?
It's very alpha. It's very alpha. This is very much a research project. I mean, we wrote a PLDI paper on it. We want people to use it. I should say it's in an alpha phase, but the PhD student who's working on it is a really good developer. So it's actually pretty solid. It's yeah, but still, it's not, you know, but it's still we want to get more people to use it. Yeah.
Okay, thank you.
Uh, Thank you for your talk, Professor. So my question is a little bit about the implementation. So the Rust compiler has its own like parser and type checking system, right? So how much of the compiler do you leverage? So I'm asking this because like right now there's only one popular Rust compiler that the Rustlang org maintains, but
Yeah.
you have compilers like GCC Rust coming up, right? So would it just work with another
It would
implementation?
not.
It
This
would
is
not.
very closely tethered to Rust C in that we use so all the analysis that I showed you
Yeah.
is it sort of works at the, I don't know how familiar you are, but it works with something called mir, which is one of the IRs that Rust C sort of crunches their code down to.
Okay.
So yeah, so all of this stuff builds heavily on the Rust C API. So it's very closely tied into Rust C right now because we don't want to do any type checking ourselves. It's just Rust C does all the plain Rust type checking, and it just gives us this mir, and then we work on on that IR, right? So yeah, it
So,
would not work with GCC at all.
so do you have to go all the way to LLVM IR to check some things, or does it happen before that?
No, it happens before that. So Rust has a whole pipeline, right? They have source, and then they have like multiple IRs. But at the MIR, it has a whole bunch of type information. It's much higher level than LLVMIR. LLVMIR is way low level, right? Everything is just like pointers to memory and so on. By then, we've lost all the ownership stuff. So here, this is somewhere in the middle. It's kind of close to syntax, but it's still like control flow graphs, and there's jumps and go tos and so on and so forth. So it's somewhere in the middle. But that's where a lot of the analyses around Rust are supposed to be targeted, and that's what
Thank,
we use. Yep.
thank you.
Uh, Thank you so much for the talk, sir. I think I learned quite a bit about programmer-aided analysis. So
Yep.
one of the questions was the same as him, how much of the Rust compiler are you leveraging? But I also wanted to ask you about, I get that Flux is different in the sense that it's programmer-aided and you, like you said, tuck in tests as you're coding. But I did use Rust for like a very short time, and I came across this thing called Chalk, which is basically a trace analysis engine, right? If I'm not wrong, I get that it's not the same as Flux in implementation because you don't do it while when you're developing. When you're writing code, you can't tuck in tests, but if I recall correctly, it uses a Prolog like logic instead of an SMT solver. So have you thought about integrating Prolog like logic into Flux as well? Because that might be more elaborate, right?
Right. So I was just trying to think. Chalk is so I think Chalk, as I recall, is a kind of a core sort of re-implementation of the Rust's own trait checker. Right.
Yeah,
So it's the
exactly.
logic. So as you pointed out, a lot of languages that use traits or type classes and so on, it's sort of prolog in the back end, right? It's prologuing
Yeah,
constraints. So you are
exactly.
correct about that, but that's a very different. It's a much I want to say somewhat simpler in that you don't have program values and you don't have these relationships between program values, what is called dependent type. So it's somewhat orthogonal to what we are doing. That being said, I will point out that if you look at the constraints that I showed you, the funny thing with the implications, that's actually a generalization of what Prolog does. So they're
Okay.
called horn clauses, and it's very much a generalization of what Prolog does. It's a bunch of constraint. Yeah, I mean, I can, if you write to me, I'll send you a link to the paper. But it's
Okay.
very much just it's Prolog in disguise, except
Mhm.
it's Prolog plus SMT because we want to do this kind of arithmetic reasoning and other kinds of reasoning, right? So constraint horn clauses are basically horn clauses are like Prolog, and constraints means Prolog plus extra kind of arithmetic equality and so on and so forth. So there is a very tight connection there as well.
Also,
Yep.
all these tests are run during compile. Like I saw, like when you were coding itself, it did throw quite a few errors as you showed. It showed a few type constraints, and it's like
Right?
this isn't satisfied. So does this actually work during like when I'm developing? Do I see these errors during compile time as well? It won't let me compile, right?
Yeah. I mean, I
Yeah.
was showing you the errors at I mean, it's in the IDE, right? So it's
Okay.
just as you go. Yeah,
Okay.
it's happening at happening at edit time really. It's just
Okay.
like compile on save, right? So it's just like Rust-C. It's basically running right after Rust-C. So Rust-C does its business, then Flux comes in and literally adds
Okay.
more errors if it has to say anything.
So there's a CPU runner, I'm assuming, that runs the code at every save, and
Exactly.
does it use anything like a JIT compiler or something like that? Uh,
There's no
to,
JIT. It's just Rust-C. It's
is
really
it?
a what is called a plugin to Rust-C. So right after Rust-C does its business, it then calls out to Flux and says, "Hey, do you have anything else to say?" And
Okay,
then
okay.
Flux kind of crunches away, and either it says yes, it's all good, or it says no, I don't like this because it produces some error, right? So it's
Okay.
what is called a compiler plugin.
Okay. Yeah.
Yeah.
Thank you so much.
Wonderful. Any questions from the audience? Yeah, I see Vaishnavi raising her hand. Vaishnavi, please go ahead.
Yeah, hi Ranjit. Thank you so much for a great talk. So I just
Welcome.
had one question about the decidability of the constraint solving and the type checking. So from what I can see, you're kind of basically embedding lambda calculus into your type language. Are you?
No, I'm
And if
not.
you are, then what's the decidability scenario?
So I'm not. So I mean, in the interest of time, I didn't get into all of that. But the long story short, I am a kind of a decidability purist, as it were, where if I, as you can imagine, for various reasons. One is just, I guess, for philosophical or whatever reasons. I want things to be decidable. I don't want the thing to kind of run away. Two is I'm just going to give you my boilerplate rant on decidability. And two is, as you saw when I did that Sherlock Holmes thing, I was making a lot of SMT queries. Right? I mean, I'm showing that as an example, but in the course of type checking a program, it makes hundreds of thousands of SMT queries. And so I cannot, if you are in this land where some of those queries are like coin tosses and I don't know, then it's just, I mean, the whole system is quite unusable, right? Because I mean, who knows what results you'll get. So, as a matter of fact, the refinement language, which is to say the stuff that you can write in purple, is very tightly constrained to fall in the fragment of what SMT solvers can handle nicely. So, arithmetic, uninterpreted functions, and
Yeah,
that's
I
really what
noticed
SMT
that you
solvers
said that if you add for all, things get complicated. So I assume
exactly.
that, right.
I do not let you write for alls. So you cannot write for alls in any. So all the refinements are in the happy fragment for SMT, and so everything works really well. And even there, I mean, I know Saurav has a lot of experience with doing things with bit vectors. SMT solvers, they do handle bit vectors in theory, but it's kind of like flipping a coin because very simple things and it just takes like 6 minutes and it can time out. So we allow them, but anyway, I'm not very happy about them. But sometimes, it's nice. I mean, you need to reason about bit vectors. What are you going to do? But anyway, to answer your question, Vaishnavi, a lot of this design, I didn't go into it in this talk at all, but a lot of it is to make sure that all the queries that are sent to the SMT solver fall in the decidable fragment. And we really tie your hands. So relative to a lot of other tools like Proosty or F star or so on, they don't care about decidability. They're like, for all, just throw the for all at the SMT solver, it'll sort it out. And I just, that is, I'm morally opposed to that. So it's very carefully organized to not allow that.
Right.
Um,
Yeah, that's why
yeah,
I asked because I have experience using F star and basically it just says I will throw my hands up if you
yeah,
send me something bad. So
right.
yeah.
And I've had fights with Nick. I always like the earlier other versions of this talk have a thing where this is a decidable logic, and Nick and Rustan Linus, Ranjit, why do you care about decidability? Like, guys, uh,
Yeah, no, I get
you
it.
think?
Yeah.
So,
Thank you so much.
yeah, you're welcome.
So I have, perhaps as the
Yes.
last question, I have one follow-up to that. I mean,
Yeah.
yes, I mean, you talk about bit vectors and somewhere in your talk you said, you go fast and loose with overflows and stuff like that.
Right.
So, and some of the questions, like some of the examples that you showed, I was wondering, like, they may not hold if there was overflow. So how are you tackling that?
So the overflow is the 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 way the overflow thing works is, there's like a little flag that I can set. So for various integer things, by default what we do is we care about underflows. So if, for example, I have a U size, or I'm not going to try and spin up the demo, but we care about underflows because that's a more like, okay, let's just rewind. The long story short, what you can do is you can imagine that for U32 you have some upper bound, like a symbolic upper bound. And if you really want to do overflow checking, you basically have to check that every time I increment a number I32, that it's still less than that upper bound, right? And so it just makes the specs more tedious. That's really it. But for example, if you know that my integer is bounded above by the size of a vector, then you can use that to show that there's no overflow. So it's not so bad. It's just yeah, overflows are not so bad. It's just a matter of picking the defaults for your plus, minus, etc. operators. And so that's a kind of flag. That's an environment variable in the tool. And by default for this demo, we just have that switched off. So it's not so bad.
So are you using integer arithmetic in your solvers or are you using bit vector arithmetic? I mean, I guess.
It's integer arithmetic. I'm not using bit vector arithmetic at all. So it's
Okay.
just all linear arithmetic. It's just integers. It's
Right.
only if in fact, if I want to do bit vector things, I have to sort of I have to use a special type, which is indexed by bit vectors, right? So by default, it's not doing bit vectors at all. It's using integers because the
So
bit
then
vector stuff is too slow.
it's both, it can be both unsound and incomplete, right? In that sense.
Correct. Exactly. Exactly.
Okay, great. Any last questions? Okay, I think we are also very much out of time. So thanks a lot, Ranjit. It was wonderful to thank you for accepting our invitation once again. If you were here in person, we would have probably thanked you with some gifts or something, but accept a virtual gift from our side.
Well,
Uh,
thank you
uh,
very much. Yes. Well, thanks for inviting me, Saurav. This was a real pleasure. And whenever I'm in Delhi next, I will come and visit you. I,
and collect your gift.
oh yes, and collect my gift. Okay, very good. Okay.
Okay, thanks, thanks.
Thanks, everyone.
Okay, bye, bye.
Bye.
Great. Thank you everyone who's joined online. Yeah, we are